Part C. Test for concavity inflection points. So we need the second derivative. The second derivative should be negative 4 sine 2x, so that equal to 0, or undefined. Again, this derivative will not be undefined anywhere, so therefore we're just looking equal to 0. That would mean that 2x has to be equal to k pi, because we know that is the type of angle, right? This type of angle there that makes the sine function equal to 0, k pi, where k is an integer. If we take a few representatives of this set, we'll get something like 2x equals maybe negative 2 pi, negative pi, 0 pi, 1 pi, 2 pi, and so forth. Solving for x by dividing by 2, we'll then get a slightly different set, negative pi on 2, 0, pi on 2, and pi, and so forth forever. Okay, so these are, at least in theory, possible inflection points. But we know that the original function was only defined over negative pi on 2 to pi on 2. So this eliminates a lot of these immediately. So all that exists within the ellipsis here up until negative pi, and all that exists in the ellipsis over here from pi onwards. So we have these three left. And even within these three, even though they're all part of this interval, nevertheless, the endpoints are negative pi on 2 and pi on 2. And there's no way you can have a possible inflection point or an inflection point at an endpoint, because there's no function after this location. There's no function going on over here to say it has a new type of concavity that was a change from what you had before, because there's nothing over here. So therefore, even pi on 2 and negative pi on 2, even though they're in this interval, and in theory they might be possible inflection points because of certain definitions, in practice here they cannot be an inflection point at all. So therefore, 0 is really the only case we're worried about. So x equals 0 is our possible inflection point. All right, so now we just need to do another sign chart for the second derivative. Again, it's the exact same methodology as the first derivative test, just yields different information because you're dealing with the second derivative instead of the first derivative. Change this a little bit here. Sorry about that. Here. There's negative pi on 2, and our one possible inflection point of 0 sitting right there. All right, now we need to figure out the sign of the second derivative across this interval on each of these two subintervals. So we'll take a test case of, over here we'll take negative pi on 4. Okay? So negative pi on 4 back into the second derivative would give us negative pi on 4 times 2 is negative pi on 2. The negative can move outside the sine function because the sine is an odd function. So the negative joins this negative out here, making it positive. Now we have 4 positive, 4 times sine of pi on 2. Sine of pi on 2 is 1. So therefore, this is just 4. So when we took a test case of negative pi on 4 from this interval, we got positive 4 for the second derivative. So the second derivative is actually positive on this entire interval, barring the negative pi on 2 value, because we saw that was one that actually makes it 0. Okay. Now we take a value to the right of 0, between 0 and pi on 2, like pi on 4, the exact opposite we just selected a second ago. So, put pi on 4 in here, you'll have sine of pi on 2 is 1 times negative 4 is negative. So therefore, this is negative. Therefore, the original function is concave up on the first interval and concave down on the second, again, barring the endpoints, because their second derivative is actually 0, not positive or negative. So we should be able to say now that we have a concave up interval from a negative pi on 2 to 0, not including the negative pi on 2, and concave down from 0 to pi on 2, not including the endpoint of pi on 2. And we have a point of inflection at 0. Which I guess is part D. at 0, comma, if we look back at the original function was an odd function. It was, what was it, x plus sine 2x, if I remember correctly. So therefore, that will be 0 plus 0 is 0. And again, because it's an odd function, you would know that it must be at the origin anyway when x is 0. Okay, so there's our point of inflection.